So welcome everyone to BrainMap. As you know, this seminar series is co-sponsored by the P41 funded Center for Mesoscale Mapping housed in the Martinos Imaging Center. So it is my great pleasure today to introduce our speaker, Professor Matthew Brookes. Matt Brookes is a professor of physics at the University of Nottingham, where he leads a research program on the development and application of human brain imaging. He is also a director and chair of the company, Circummagnetics Limited, which builds novel brain imaging equipment. His work and that of Circummagnetics has won international acclaim, most notably awards from the Blavatnik Family Foundation and the UK Institute of Physics. So without any further ado, I'll hand it over to Matt. But before I do that, Matt has said that he would welcome questions anytime. So please feel free to just raise your hand in Zoom or just type your question in the Q&A section, and we will get to it. We are actively monitoring the comments. So Matt, I hand it over to you, and thank you so much for being with us today.
Thank you very much, and thank you for the invitation to speak today. And so just to check, is somebody else monitoring the chat in case there are questions, because I might not see all questions. Brilliant. Okay, so just stop me if there are questions by all means. So today I wanted to give you an overview of some of the work that we've been doing on developing and applying magnetoencephalography or MEG. So by way of overview, I'll start by introducing what MEG is, the basic principles, and I'll talk through a few of the clinical applications. But then actually, rather than sort of talking about how wonderful MEG is, I actually want to talk about its limitations. I'll then go on to talk about optically pumped magnetometers, which are new types of magnetic field sensor. I'll talk through their basic physics and say a little bit about how we've been using OPMs to design a new generation of MEG systems. And I'll finish down the bottom here with some recent examples of some of the studies that we've been doing, in particular a study in children, and I'll say something about the next steps in our development. So, MEG, many of you will be familiar with it, but just in case anybody isn't, MEG is the measurement of magnetic fields generated by current flow through assemblies of neurons in the brain. So if this is up here, we've got a dendrite of a neuron. Currents flow through those dendrites. Those currents generate magnetic fields that are given by the white lines here. And those magnetic fields happily pass straight through the skull, and they exist outside the head here. So this here, the red would represent a field coming out of the brain. The blue represents a field going back into the brain. And so if we can get sensitive enough detectors placed around the head in an array a little bit like this shown here, we can measure those magnetic fields. We use a system. This is a conventional MEG system. It looks a little bit like this. You put your head in this helmet and you measure those magnetic fields that exist around the head. Of course, magnetic fields themselves are not actually that much use. So what we do is we take those magnetic fields and apply a whole bunch of mathematical trickery that So yeah, we measure these magnetic fields that are generated around the head, and then we apply a bunch of mathematical trickery that I'm not going to talk about today, and we can turn these magnetic fields into images showing the spatial distribution of brain activity. So we can look at the inferred current flow in the brain, and we can do that millisecond by millisecond. So we can look at the evolution of brain activity in real time. So that's what MEG is. And it has lots of different applications across the whole range of sort of neuroscience. Clinically, you might have come across it in the context of epilepsy. So in epilepsy, we see these things called interictal spikes. So this is an example of some data taken from a recent paper that we published with the Children's Hospital of Philadelphia. So each of these little spikes marked in red is an epileptic event, an epileptic spike. So they're abnormal, they shouldn't be there. And what MEG is often used for in epilepsy is we try and localize the origin of those spikes. And that, in this case here, we can see this yellow blob is the origin of the spikes. And that tells us a little bit about the brain region that's generating seizures in an epilepsy patient. Now, you can try and do this with EEG as well, but EEG doesn't have as good a spatial resolution. So this is probably the best non-invasive way to localize epileptogenic cortex. Again, this is just a simple example, but so here the yellow dots are the areas where the MEG localized epileptic spikes to, and here this is the post-operative MRI showing the area of the brain that was resected, and you can see that the two line up really nicely. And there's now pretty good evidence to show that that MEG really does help in patients with focal epilepsy who go on to have surgery. So that's the major clinical application of epilepsy that you might have seen before, but there are lots of other areas where it's being developed. One example area is in concussion. So in concussion, patients are most often MRI negative, and about 30% of patients go on to have long-term sequelae, but we don't really understand why MEG is being used in concussion to try and understand what actually goes wrong in the brain following a concussion. So this is work that we did here in Nottingham with Nicholas Evangelo, Chris Allen, and Lucas Rea. And what we were showing here is that actually connectivity, so we can measure electrophysiological connectivity between different brain regions using MEG, and that electrophysiological connectivity is significantly diminished in patients following a single concussion compared to our control group. So again, just another example of how MEG is being used in this case for clinical research. So I could go on and on about why MEG is a really good way to study brain function. Actually, that's not what I want to do. I want to talk about its limitations. So here's our conventional MEG system. And the first thing is all of the sensors that we use to detect the brain's magnetic field, so the sensors that are inside this big helmet, have to be cryogenically cooled. So they're superconducting sensors, so they have to be cryogenically cooled to enable superconductivity to happen. That means that sensors have to be kept quite a long way away from the head. So rather than being directly on the head surface, they're actually about 2 or 3 centimeters away from an adult head surface. So you can see here, this is an adult in the system. She fits the system reasonably well. Now, the signal from the brain decays with the square of distance. So if we double the distance, we will quarter the signal that we measure. And that means that every single centimeter that you move, or every single millimeter that you move away from the head, really does hurt you in terms of the signal to noise ratio that you can expect. And so because we're a long way away, we do get a lower signal to noise ratio. It's also a one-size-fits-all system, and it's built for adults. So what that means is this helmet is adult-sized. If it was, if you decide to scan a child or a baby, their heads are much smaller, and so the sensors are proportionally further away from the head surface, which again reduces this signal to noise. You have to stay relatively still inside this helmet. So if you've got movement disorders, or again for children, actually it becomes very difficult. So if we want to do, say, a 20-minute scan, actually somebody's got to stay still for 20 minutes inside this helmet. It's really hard to do, even if you're a healthy adult. And it's even harder if you're trying to scan a 2-year-old or perhaps an elderly person, or even just a patient who might be nervous about the scan. So we get relatively low data retention rates because it's hard for people to keep still. And the final limitation is these machines are very expensive, not only to buy, but also to run. They use liquid helium, which is an expensive, non-renewable resource. You can these days attach helium liquefiers to them, but even in that case, those helium liquefiers are expensive piece of equipment to buy and to run. They use a lot of energy. So for all of these reasons, whilst these conventional MEG scanners are a great way to look at human brain activity, they are in fact quite limited, and that's really prevented the large scale uptake in a way that's, let's say, EEG is used in every major hospital. So MEG is by and large better than EEG, but it's so much more expensive and harder to deploy, particularly in children, that it's not widely used. So our vision when we started this work back in around 2014, so almost 10 years ago now, was to turn our massive MEG scanner into something that looks more like EEG. So could we in some way take these cryo-cooled superconducting sensors and replace them with something that might look like a little Lego brick that can go onto the scalp surface and measure the magnetic fields that are generated by our brains without these huge machines. So that was the idea, and it became a reality with the introduction of optically pumped magnetometers. So these two things here are optically pumped magnetometers, or OPMs. They're both made by an American company who are based in Colorado called QSpin, who build absolutely amazing quantum sensors. I wanted to say a little bit about how these work. Not too much. By all means, you can ask me the detail if you're interested. But essentially, each one of these sensors, this is the one we use now, relative to a pound coin. So it's about the size of a normal Lego brick. Inside that sensor, there is a glass cell with some rubidium atoms represented here by the red dots. There's a laser and there's a photodetector. And those rubidium atoms each have a tiny little magnetic moment. So they behave a little bit like a compass needle that will rotate in the Earth's magnetic field. Each one of these is like a tiny bar magnet, like a tiny compass needle. And at zero field, they will be pointed in lots of random orientations. What we can do is we can switch on a laser, and that laser, if it's tuned to the right frequency, that laser light, the photons in the laser will be absorbed by the atoms. And one of the things that we can do is absorb photons in such a way as to align the magnetic moments of these rubidium atoms with each other. So rather than the rubidium atoms' magnetic moments pointing randomly, they now point all along the same direction. Once they're all pointing in this direction, they can no longer absorb photons, and so our gas becomes completely transparent to the laser light. So the intensity of laser light at the photodetector is more or less the same as the intensity of the laser light that was emitted by the laser. So the intensity of the light that we detect over here is a maximum. And I said this happens at zero magnetic field. But now if we were to introduce a human brain, so that brain is now generating the magnetic fields that we know we measure from MEG. So we get this neuromagnetic field that's crossing through the glass cell. Actually, that will cause the atomic magnetic moments to deflect. So they all point in the same direction, but they all move. And now they can start absorbing the laser light again. So actually what we get is a dip in the intensity of laser light at the photodetector. So if we measure the amount of light at the photodetector, that tells us a little bit about the magnetic field that's impinging on this glass cell. And what we can do is we can use that as a very, very sensitive magnetometer. And that's in effect how these sensors work. So that's the sort of slightly hand-wavy description of how an OPM works. Again, if we want to go into the physics a little bit more detail, we absolutely can. So we've been using OPMs now since 2016. We started this work, well, it was published in 2016. We started in late 2014, early 2015 by looking at simulations. We got our first OPM from QSpin in 2016, 2017, and we were working with Gareth Barnes and his team at University College London. And we made the first measurements with this OPM. It wasn't the first measurements that had ever been made measurements that had ever been made with an OPM. I think they were probably the first measurements with a commercial QSpin OPM. So we made these measurements in 2017. By 2018, we had a wearable array, and I'll talk a little bit more about that later. So this was an array that you could move around in. As you can see, between 2018 and 2019, the sensors became smaller, so to these Lego brick size sensors. By about 2020, we had a whole head system of these little Lego brick sensors, and this is where we are now down here. With we've got 192 channel meg system. So there are 64 sensors, and each sensor measures magnetic field in 3 orthogonal orientations. So 3 times 64. So we have 192 sensors, and these are the systems that we're now using. I always like to show this just to show what you can do. This is what we mean by a wearable system. So this was a very early study published in 2018, but it sort of shows the idea. So here you can see brain activity superimposed onto an anatomical. So the blue blob here is the beta band response, beta oscillations to movement, and so you can see that here our subject was able to carry out a naturalistic task, playing ping pong, and sure enough, we were able to localize changes in beta band. So this is a time frequency spectrogram showing time in the x-axis, frequency of neural oscillation in the y-axis, and we can see a really nice desynchronization of the beta band throughout the 10-second task. And you can see that she was actually moving her head reasonably naturally here, and we'll talk a little bit about that later. So that's the introduction, the sort of basic idea. I wanted to talk in a little bit more detail about how we actually design the sensors and the sensor array. So this is a conventional OPM. This is what I've described. So we have a laser beam going through a glass cell to a photodetector. And actually, this would enable you to measure 2 magnetic fields. We could measure the magnetic field in X, and we can measure the magnetic field in Z, but we can't measure the magnetic field in Y. So along the direction of the laser beam, we're not particularly sensitive. So that's a limitation, that these conventional OPMs can only measure in 2 orientations. We can't measure along the direction of the laser beam. But of course, if we have 2 laser beams, so we have a laser beam running in Y and a laser beam running in X. So now with our top laser beam, we can measure X and Z, and with our bottom, we can measure Z and Y, and then we can combine these things together and actually get a complete 3-dimensional picture of the magnetic field outside the head. So we were working with these sensors from around 2022. So prior to that, we'd been working with these dual axis sensors, so measuring 2 components of magnetic field. We were really worried that by splitting the beam, so we've still got a single laser and we just split the beam with optics. We were really worried that this would increase the noise, but actually it didn't. This is the triaxial QSpin sensor. This is the noise floor. So we want that noise floor to be around 15 femtotesla per square root hertz. The gray background is what we see with our conventional dual axis sensors, and the three colors, the red, the blue, and the yellow, are our three axis sensors. And sure enough, so that's the X, the Y, and the Z components of our three axis sensors. And actually, they're at the upper end of where we would hope them to be, but actually they're still within our 15 femtosecond per square root hertz sort of wish list, if you like. So and that was more than good enough. So these were the first measurements we made, first measurements of brain's magnetic field, first MEG measurements that we made with these sensors, and sure enough, we could see, you can see here, magnetic field being generated by a dipole in the brain. So we can measure with triaxial sensors, but why might we want to? Does it tell us anything more about the brain's magnetic field? Well, it does a little bit, but actually the real advantage of triaxial sensors is that we can much better characterize fields that aren't coming from the brain. So here I've got a schematic of two different fields. This one, the top one here, is supposed to be coming from the brain, and you can see it's swirling around a source that might be inside the head. And here, this second one is a uniform field that's coming from somewhere outside the brain. And so actually, if we can only, so we've got three sensors represented by the three circles here. If we can only measure the radial component of field, which is what a conventional MEG scanner measures, then here we'd measure a field going out of the head on the left-hand side. Our top sensor here would measure nothing because it can't measure tangentially. And our third sensor here, sensor 3, would measure a field going into the head. And that's for an internal source in the brain. Actually, if we look at what that array would measure, if it could only see radial sources, radial fields, sorry, for a uniform field generated outside the brain, well, actually it measures more or less the same thing. So these two very different fields look very similar if we can only measure radially. But actually, of course, if we can measure all three axes, then we get the fact that they're very different. And this actually manifests, so this is a simulation study where we compared 50 radial sensors, 150 radial sensors, and 50 triaxial sensors. And we looked at the similarity between magnetic fields generated by the brain and magnetic fields generated by interference. And actually what we showed is that there's a dramatic drop in the similarity between brain fields and interference fields if we use triaxial sensors. So actually this is a really neat way to cancel magnetic fields coming from external sources, so interference. And here we can actually see it in action. So this is a radial reconstruction. This stripe that you can see in the reconstruction, so the big yellow blob is real brain activity, but there's a stripe that you can see before that, and that's a 16 hertz artifact caused by an air conditioning fan in our lab. And actually, if we use triaxial reconstruction, we can see that nasty artifact goes away. For anybody who is familiar with MEG, one of the ways that you can exploit this is with something called SSS or max filter. So those of you who have used SSS or used MEG might well have come across SSS. Actually, the performance of max filter is characterized by an angle, which so what SSS does is tries to differentiate sources from the brain from external interference, and you can write down an angle which details how well you can separate these different sources, brain sources and interference. And for a MEG array, those angles are about 10 to 15 degrees. And of course, what you really want them to be is 90 degrees, because then you could separate them perfectly. And actually, so with dual axis OPMs, we get to about 40 degrees, and with triaxial, we're getting to about 60 degrees. So we're opening up that angle. So that's an aside for those of you who are familiar with MEG and SSS. Another reason to use triaxial sensors, because you've got effectively more channels, you start to fill in, you start to get better coverage. So this is the coverage in an adult with radial sensors. This is the coverage with a 4-year-old, and this is the coverage with a 2-year-old. And so you can see with radial only sensors, actually you get these sort of horrible speckled patterns of sensitivity, and it gets worse as you go to younger subjects, because as you go to younger subjects, you're getting the sensors closer and closer and closer to the brain. So you can see these are MRIs, real MRIs, and you can see in these young subjects, the brain is very, very close to the edge of the scalp, whereas in adults, it's a bit deeper. And because you get so close to the brain, actually you start to spatially alias the brain surface. Whereas actually, if we look with our triaxial sensors, we get much more uniform coverage. So lots of reasons to use triaxial sensors. The other question that we get asked quite a lot is how many sensors is good? How many sensors do you need? And the answer is always, we don't really know. This is a recent study by 2 colleagues, Ryan Hill and Holly Schofield. And what they were doing was trying to look at the difference between how you pack sensors. So if you have, this would be a sparse array where we have 32 OPMs, they're triaxial OPMs again, but they're spaced all around the head. And we're trying to measure a source in visual cortex that generates roughly 60 Hertz gamma oscillations. So this is what we measured with our sparse array. We can see these gamma oscillations. There was a visual stimulus, a circular grating that was on for 2 seconds, and we can see a response here. But actually, if we take our 32 sensors and put them right over the back of the head, so they're all over the visual cortex, we can see that we get a much better response. And here it's a different study. Here we had again an array of sensors over the back of the head. This is a paradigm where people were just viewing natural scenes. So they were viewing GoPro footage from a person walking around a big city. So it was video footage. They were viewing that for 5 seconds, followed by 5 seconds rest. You can see here broadband gamma activity, really, really nice broadband gamma activity coming from the visual cortex, which is really quite nice. And then what we can do is we can turn off individual elements of this array, so we can change, if you like, the channel count, and that's what we're doing in the x-axis of this graph. So you can read the x-axis of this graph as switching on different channels, and you can see that as we increase the coverage by switching on more channels, we get a linear increase in the signal to noise ratio of our gamma band response, which is really nice. And the thing that we really liked about this is actually when we did these same experiments with our squid array, the signal to noise of the squid array was quite a lot less than what we could get from our OPM array. So this is what we would get. The pink dotted line is on average what we would get in the same participant if we measured their gamma oscillations with a conventional MEG system. So we can do much better in terms of SNR. So we're getting up to better sensitivities by using OPMs. So I wanted to say a little bit about background field control. So one of the problems is, well, one of the great things about OPMs, as I've already shown, is we can allow the head to move. So I showed that video of one of my colleagues playing ping pong. But the problem is, if the head is allowed to move in a background field, then that generates magnetic artifacts. And so here we can see as the head moves, you can see very large change in magnetic field. So actually what we want to do is we want to make a region of zero field over the helmet. Now we use these big these big magnetically shielded rooms, which does help to reduce the magnetic field, but it doesn't take it down to zero. And actually, what we need to do is to use coils. So what we do is we measure the background field in the region of the helmet, and then we have these different coils. So this is called a matrix coil. So these are multiple units of individual square electromagnetic coils, and we can individually control the current in each of these squares, and that allows us to place a magnetic field null over the OPM array, over the helmet. And you can just about see, hopefully in this photo, that the helmet's in the middle there. So what we're trying to do is change the currents in all of these little squares to place a magnetic field null over the helmet. So that's exactly what we do. And of course, as the helmet moves, we can change the current. So these are the currents represented by the blue and the red. These are the currents that we might use if the helmet was right in the middle of the array. If the helmet were to move to the edge of the array, we can change those currents to move this magnetic field null. And because the helmet is then in a zero field, it allows us to measure our meg data without getting huge magnetic artifacts because the head is moving. So this was really a key to working out how to do experiments during free movement. So this is another study recently published by one of my colleagues, Niall Holmes. And here you can see a subject who's walking around in the room. Obviously, this is speeded up. He doesn't normally walk that fast. You can probably just about see he's got some button boxes, and he was just pressing some buttons, and we were getting really nice meg data despite the fact that he was essentially walking around inside our shielded room. So that was just one example of the fact that we can actually get really nice brain imaging data even if somebody's up and walking. And that obviously has applications in things like Parkinson's disease, understanding bradykinesia, maybe in children as well. So what changes in the brain before and after a child can walk. So this is still quite technically challenging, published last year in Neuroimage, but it is possible to get good brain imaging data as people make very, very large movements. I'm going to skip over this bit because I'm conscious of time. So we've been working on this now for quite a while, and around 2020 we were being asked by lots of groups around the world, well, you know, we'd quite like an OPM meg system. Would you help us build one? Obviously, as a university, we're not allowed to just sort of help people build OPM meg systems. So we set up a small spin-out company. And one of the first people to approach us was Sick Kids Hospital in Toronto. And they said that they'd like to have a play with a meg system. Now, anybody who's ever been to Nottingham will probably remember that the university campus is effectively in the middle of a field. And there's very little in the way of infrastructure, very little in the way of magnetic interference. And all of a sudden, we were faced with building a system in the middle of Toronto. And I quite like this quote from the lab director. We've got a construction site across the street, a subway line under the hospital. There's an elevator down the hall, a parking garage underneath the MSR, and the main entrance to the hospital car park is right overhead. And the way that manifested was that the static field, the residual magnetic field inside a magnetically shielded room was around 25 times worse than Nottingham. And the field shift, so the way that the field drifts over time, was about 30 times worse than Nottingham. So this is a very different proposition, making an OPM meg system, which is very, very sensitive to background field, making an OPM meg system work in a hospital in a major city is a really different prospect to making an OPM meg system work in a campus university in the middle of a field. Nevertheless, actually we did. So we used a combination of the coils, which I've just shown you, those matrix coils. We used a system similar to that in combination with lots of software approaches. And actually, this is the data that we're getting now. So this was a paper that was published a year or two ago by one of my colleagues, Ryan. And so this is beta band envelopes during a motor task. This is gamma band envelopes during a visual task. And you can see that actually the data that we were getting in Nottingham and the data that we're getting in Toronto are actually pretty comparable now. And so we did start this sort of journey towards commercializing OPM-MEG with a small company called Circa Magnetics. We started Circa Magnetic back in 2020, and so this was that first 80-channel system that we installed in Sick Kids Hospital. We installed that back in 2021. We've since built 3 more systems, 2 in the US, 1 in the UK, and we've got 5 installations scheduled for 2024 and 2 more in 2025. So these systems are slowly slipping out into the big wide world and hopefully being used by neuroscientists and clinicians to investigate whatever they're interested in. So just in the last few minutes, I want to tell you about another study that we've been doing in Nottingham. This I find quite exciting. So this is a study in children. So this is what our system in Nottingham now looks like. It's got 192 channels. So as I've said, we've got 64 triaxial sensors. The system's housed inside a magnetically shielded room. We have these matrix coils that I've talked about that control the field over the array, so subjects can move freely during a scan. We have reference array as well, which can measure the background field. All the OPMs are controlled by a single acquisition PC, and we have a stimulus PC that can provide visual stimuli or the different types of stimuli to the subject. So this is what the system looks like. There's a photograph of it. This is work by Lucas Rear and Natalie Rhodes. This is Natalie wearing the hat. We just submitted it for publication. This was a study, as I've said, imaging children. So we use Braille stimulators. So these are somatosensory stimulators. So you can hopefully see here in the bottom right that there's 8, we call them pins. They're not sharp. They're just plastic, little plastic cylinders that can pop up or down. So they're controlled by piezoelectric crystals. So they will pop up or down, and we can make a pattern on the subject's finger. Here we were scanning children aged between 2 and 13, so we didn't want to make any patterns, so we just popped all 8 pins up or down, and the study was half a second of stimulation. In that half a second, the pins went up and down 3 times, so tap, tap, tap on the finger, followed by 3 seconds of rest. And we alternated between tapping the index finger and tapping the little finger. The kids came in, they could watch a TV program throughout the study. Their parents sat with them. Some of them sat on their parents' knee. They weren't encouraged to move, but they could move freely. So here's a photograph of a child wearing our system. And so that was the experiment. As I said, youngest was 2, eldest was 13. We also did the study in 26 adults who were also allowed to watch their favorite TV program. So this is the first child that we scanned. So just results in an individual subject. We were able to localize the area of the brain that was responding to the index finger and the little finger. In this child, not in every child, but in this child, they localized to slightly different regions, which was great. It sort of also maps with the homunculus, which was nice. We can see this nice beta band desynchronization, which is exactly what we expected to see during the presentation of the sensory stimulus. So that was a single child, just looking at beta oscillation. One thing we were very interested in was connectivity. So how does the brain's connectivity develop with age? And so we measured all-to-all connectivity. So these are connectivity matrices or connectomes. You can see each along each axis, there's different brain regions. So if we look at sort of the left motor region and look across here, the darker red would indicate the areas that were most connected to the left motor region. And if we scan down, we find that it's unsurprisingly the right motor region. So we can see that individual blobs, the sort of structure in these matrices, tell us a little bit about the connectivity, all-to-all connectivity. These glass brains at the bottom just show the top, I think 100 or 150 connections. So where are the strongest connections in the brain in adults? And not surprisingly, this is all done in the beta band. And so not surprisingly, we get sensory motor connections in adults, which is great. Actually, when we looked in the children who are older than 4 and here the children younger than 4, what we see is a very different connectivity pattern. Here in the children, we're getting very strong connectivity in the visual areas. Now we also see, so these 4 big blobs here are the visual regions. We can also just about see the blobs, those visual blobs in the adults. So we did have strong connectivity in the adults, but it just wasn't the strongest connectivity. The other thing you notice is that actually here we're going up to connectivity values around 0.2, whereas here we were only going up to connectivity values of about 0.1. So at least in principle, the connectivity in the adults is much stronger overall than the connectivity in the children, and that actually pans out. So here, in each individual blue blob represents a different subject. We're going down to age 2 and all the way up to age 34. And we can see on average, so this is the total sum of connectivity across the whole brain, and adults have stronger connectivity than children. That was expected. That's a known result, but it was still nice to prove it with our system. And the one thing that we were able to do, unlike previous MEG studies that have tried to do this, we've been able to go down to much younger subjects, down to around age 2. This is not work from our lab. This is work from collaborators, Xavier Deterge's lab, but I did want to mention it. So this is now moving back to epilepsy. This, I think, is quite amazing data. This is using a very similar OPM-MEG system in a 10-year-old child. And what Xavier and his colleagues did was to measure MEG data during an epileptic seizure. So this child was having a seizure, and they were able to measure data, even though the child was moving because of the seizure. It sort of shows here from a clinical point of view. So hopefully this shows why it's important to measure children and neurodevelopment, healthy children, and this perhaps shows why these systems are actually quite useful clinically. Just in the last minute or so, because I'm aware I'm nearly running out of time. One of the things that we're now trying to do is to change fundamentally the design of the system. So this is what we like people to see of our system. We've got a nice patient support, a nice helmet. You can put that helmet on and people can move. What you don't see is that underneath that helmet, there's 64 channels. There's 64 sensors. So there's 64 big cables coming out to a massive, great big set of electronics. And going back to the guys at QSpin, the QSpin Vision back in 2022 was something more like this, where all of the electronics, all of this big electronics rack, which stands about 8 feet high, that big electronics rack is contained within this backpack, and people could maybe go for a walk around the shielded room whilst wearing this backpack, and it becomes a fully portable system. So that was a QSpin Vision back in 2022. This is the sort of 2024 reality. This is a system that we've got in Nottingham now. So all the electronics really is in that backpack. We've got rid of this huge rack of electronics. all of the system is in the backpack. Obviously, it's a bit of a tangle of cables at the moment, but that then connects to the head-mounted sensors, and so it's improving wearability. So rather than just the helmet, now the whole system is wearable. There's just 2 cables that come out of this backpack, and so you can much easier go for a walk. We could perhaps get older people walking on a treadmill, or maybe even children walking on a treadmill, and looking at the brain activity. Just comparing the 2 systems, we're getting very similar results. So again, we've got visual gamma and motor beta activity, and we're getting very similar results with our backpack system as we were with our massive rack. So that's sort of where we're heading. So just to conclude, hopefully I've been able to convince you that our quantum sensors, or our OPMs, can get do quite a good job. They get much closer to the brain than conventional cryogenic sensors, and if we use enough of them, that means that we get higher sensitivity. And we also get, what I haven't shown today, but there are papers out there to show you can get better spatial precision as well. Because the sensors are so small, we can put them anywhere, and that allows our system to adapt to any head shape, which is quite good. It means we can scan anyone from babies to adults, and hopefully I've convinced you of that by showing our data going down to 2-year-olds all the way up to adults. The sensors do move with the head, so we can measure people while they move freely, although that is very, very dependent on our ability to control background fields, and so we do have these sort of quite complicated coil systems, but they seem to work quite well. And when we've controlled the background field, we are able to scan people while they're walking around the room. And even at this early stage of development, the new OPM systems are probably less than 50% of the cost of a conventional system, and they're also modular, so they do go down to quite low costs. So I'll stop there, apart from saying obviously all this work was done by a huge team of people, both at the University of Nottingham, at our spin out Circa Magnetics, and all of our collaborators around the world, and a special thanks to all the guys at QSpin in Colorado, who are absolutely amazing in building our sensors. So I'll stop there. Thank you very much again for the invitation. Thank you for listening, and very happy to take any questions.